Okay, we've now defined a one-dimensional transform of the cosine transform. It's time to see how we can extend this to 2 dimensions. Well, since we've been talking about n-dimensional things all along, this may seem trivial, but remember we already have, in the case of the cosine transform, essentially an infinite dimensional signal because it's continuous. And so now we're continuous in 2 directions, and this gets a little bit trickier. So I'll walk through how we're going to build this up, and this will apply to other things as well. So first off, we're going to start with our single dimension transform, our psi k of t's, k greater than or equal to 0, and that will be our cosine 1 basis that we've already talked about. Then we're going to define or set psi 2t k1 k2, and we have 2 time variables now, so we'll have one be s and the next one be t, and we'll just say that this is equal to our regular cosine basis multiplied together, so it's separable. If it's separable, can we really model everything? Well, we'll see. Watch this. Okay. Then our psi 2d k1 k2 s comma t for k1 k2 in the counting numbers is greater than or equal to 0 is an orthonormal basis for L2 0, 1 squared. In other words, the square from 0 to 1. So I should note that this is true in general. That is if phi k of t is an orthobasis on L2 0, 1. Then phi k1 k2, defined in the same way we just did, is an orthobasis on L2 0, 1 squared. Okay, so how do we show that? What do we do? Let me outline the general proof, and you can finish this up in the homework. But first, let's illustrate what's going on. So we have I'm going to use a different color. we have our space from 0 to 1. Like so, approximately 1, 1, 0. And we have several things we have to show. First, let's put some signal in here. Okay, so I admit I'm having a lot of fun drawing these signals. Okay, there we go. So we have some signal, and the first thing we need to do is show that in this case we have a double integral. Phi k1 k2 s comma t times phi L1 L2 s comma t ds dt is equal to 1 for k1 equals L1 and k2 equals L2 and 0 otherwise. So that's step 1. And since we have phis, or in the special case of the cosine transform, we've defined it as these psi functions that are separable, then this whole operation becomes almost trivial. Okay, next we need to show that that phi k1 k2 s comma t spans 0, 1 squared. Okay, so this is part of the next homework, but let me outline just a few of the steps that you're going to have to go through to do it, or how you might go about doing this. Because I found in past years that everybody's going to need help, so I may as well give it up front. Actually, there's a few of you that could probably get by without any help, but and I've robbed you of the chance of showing that you can succeed on your own. So if you're one of those people, now is a really good time to stop watching the lecture. Okay. So show that these are orthonormal, as we've talked about above. Step 2. And this is really the trick. Assume that S is fixed at S is equal to S0. So what that looks like up here is we choose some well, I guess I'll choose that one. Choose some S0 right there. So this would be our S-axis and this would be our T-axis. And we say that S is fixed there. And So if we're looking at x, our 2D function, then we can see that this is only a function of t. And we already know, since we have an orthobasis, that we can do that. Now, if I go too much further, I'm going to tell the whole thing. But this is really a function of S naught. Well, if we have something that's a function of S naught, it can be decomposed. Using Vk or L2 or whatever of S. So it's in two steps. We assume we're looking at a particular row. We can decompose that, and then our coefficients now become a function of where that row is. And so we can decompose them because they're different functions. So that's the basic idea behind the 2D cosine transform. And also a hint to help you out with homework 4.